Assalamu alaikum. In this video, we'll be learning about the probability distributions. We'll also have a look at the discrete probability distribution. Probability distributions are mathematical functions which define the probability for a random variable for all possible values that it can achieve. There are well-defined parameters which are associated with most of the distributions, since the distributions are mathematical functions. So just like any mathematical functions can have parameters, the distribution functions also have parameters associated with it. The probability functions are known as probability density function if you're working with continuous random variable in case of continuous distributions, and probability mass function for the discrete distributions. The probability distributions are plotted for easy understanding and quick analysis. We have seen some probability distribution plots earlier, and you can recall that at first glance, you can find many things out of the plot. So plotting probability distribution function lets you make quick analysis, and those can be used for some basic decision making. Many popular probability distributions exist. Some of them are uniform, normal, binomial, or Poisson, and there are many others. Let's discuss the discrete probability distributions and specifically the binomial distribution. Before that, we need to understand what a binomial experiment is. A binomial experiment needs to have these four characteristics for it to be called as a binomial experiment. So in a random experiment which has these characteristics, the first one and most essential is that if the experiment is repeated for a fixed number of trials, each trial is independent of the previous trial of each other. So this, in simple words, means that the outcome of one trial is not going to affect the outcome of the next trial. So they are conditionally independent. Then the outcome of trials can have only one of the two outcomes, either a success or a failure. This is the reason they're known as binomial, because they have only two nominal values, success and failure. The probability of success is the same for each trial. And this is going to be true if the independence condition is met. Because when the trials are independent, every time the probability of success is going to remain the same as it was for the previous trial. The random variable in binomial experiment counts the number of successful trials. Examples can be observing the number of students who pass the final exam out of a class of 30. So this is actually a binomial experiment repeated 30 times. And we are actually finding out the probability of a certain number of students passing this exam. We count the number of students who passed this exam. Recording the probability of defective products manufactured from a 15-item lot. Again, we observe 15 items and find and count the number of products those were found defective. The random variable, the binomial random variable can take on the values of all the possible items that could be found defective in this case. Reporting the number of customers, leaving a positive review from a list of 10 customers which are randomly selected for an online shopping website. Now let's see which of these experiments are binomial or not. Observing the colors of headscarves for the randomly selected 10 girls entering a mall. This is not a binomial experiment. The reason is we need to have four conditions met. The first one is for the trials to be independent. The second is that the outcomes should be either a success or failure. Here, the outcomes are the colors of the scarves. So we cannot qualify them as a success or failure. For this reason, this experiment is not a binomial random experiment. The next one is recording the number of children who are bringing home cooked food for lunch on Monday from a sample of 15 randomly selected children. It's already revealed this is a binomial experiment. Why? Because we have two outcomes, yes or no, either bringing home cooked food or not. So success failure criteria is met, and what one child is bringing is independent. It is practically independent of what another child would be bringing. So those are independent. The probability of someone bringing food, home cooked food, would generally be the same. So we can consider this as the binomial experiment. Recording the girls to boys ratio in schools of Rawalpindi. This experiment is not a binomial experiment. but the reason that the outcome is not success or failure, rather it is a continuous value. Recording the number of schools with higher strength of girls than the boys out of a randomly selected set of 20 schools. Here, this is a binomial experiment because now we can have yes or no, which is a binomial outcome, which is success and failure, and the probability in a certain area for girls being in a higher proportion than boys remains the same. And what happens in one school is independent of what happens in another school. So the independence condition is also met. Recording the native cities of candidates appearing for interview for a job at a software. This is not a binomial experiment because the outcome is not binomial, rather it is the qualitative value, categorical values, which are the cities from which these candidates are coming. The binomial distribution is the distribution of a discrete probability, a discrete random variable. It records the number of successes in n trials of a binomial experiment. So the first condition is that there needs to be n trials. And then binomial variable can take on all the possible values that could represent successes in those n trials. So of course, that could be range from 0 to n. You can have none of the trials being successful or all of them being successful. And then the entire range between them can be the values that this binomial variable can acquire. The binomial random variable follows the binomial probability distribution. The probability mass function for binomial distribution is given by this. We can take some time to see different parts of this PMF. We are basically trying to find out the probability of X successes in N trials. So say, for example, if we are repeating a trial, such as we are trying to count the number of female students who enter the university gate on a certain day, our success is that someone who enters is a female student. So we count it as success. And we do it for 50 students. Here we have 50 trials, so the N is 50. And we are trying to find out the probability for a given number of successful trials. So if we want to know what is the probability that 30 out of 50 students will be girls, we are going to substitute the value 30 here. And then this function is going to give us the probability of 30 successful trials, which means 30 students out of 50 being girls. How we calculate it is like this. We have combination. We choose the number of successes as X here and number of trials. So in our example, 30 will be substituted for X and 50 for N. We multiply it with P raised to power X, which is the success, the probability of success raised to power the number of successes. Let's first see what these different values in this function they represent. N is the number of trials of the experiment, which we have seen, but P we do not see already. P is the probability of success. What is the chance that we'll have a success? So if you have equal number of girls and boys in the university, the probability of success, which means probability of finding a girl in the example that we're considering, would be 0.5. But if you have more girls than boys, this probability can be greater than this value. But whatever the probability is, it should remain the same for every trial. So every time the next person is entering the university, the probability of her being a girl or being a boy should remain the same. So P is the probability of success. Q is the complement of that, which is the probability of failure. X is the number of successful successes considered, the value of random variable for which you're trying to find out the probability. In our case, we wanted to know what is the probability of having 30 girls among the 50 people who were observed. So in our case, X is equal to 30. Now, when we can substitute these values here. So this is P, the probability of success, raised to the power X, which is the number of successful trials that we are considering. And Q is the probability of failure, which is complement of P, and it is raised to the power of N minus X. And N minus X are the number of trials which were not success, which were failures. So In our case, it is going to be the number of people who are not girls. Binomial distribution has two parameters, which are n and p. So if x is a binomial random variable, then we specify this as this fact as this expression, which is x is follows binomial distribution with these parameters, and we substitute the values of n and p for that specific case. Let's consider an example here. X here represents the number of sixes in n trials. This example is basically rolling a die 10 times. So the trials are n here. Number of trials are n. And we want to find out the probability of getting sixes over the range of trials. The value that x can take on is 0, which means none of the trials give 60. None of the times we got 6, sorry. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 means all of the trials met success, which means we got sixes in all of the n trials. So n is 10 here. Probability of success is 1 by 6. How we know that? It is every time you roll a die, a fair die, the probability of getting a 6 is only 1 by 6. And this is the same for any of the other value that you can get. So here, the probability distribution has been plotted. For 0, this value is computed using the same probability mass function that we saw earlier. And it is, we substitute 0 for x, and we substitute these values for all of these variables listed here. And these probabilities have been calculated and plotted. So you can see that the highest probability is to get either 1 or 2. It's somewhere with just 1 success in 10 trials, 1 times get a 6, or 2 twice get a 6. The probability of getting 6 times 6s is very low, and higher than that is almost negligible. Let's do this with the help of an example. 10% of the computing students of a certain university know at least 3 programming languages. If 10 students are selected randomly, what is the probability that 5 of them know at least 3 programming languages? So this is clearly a question of binomial experiment, because when we're making the selections, they're random. So the probability of the next student knowing or not knowing the programming language is independent of what was the outcome, what was the answer of the earlier student. Secondly, there are 2 outcomes. Either a student knows at least 3 programming languages, or they do not. So we can model it as binomial random variable, and we define x as the number of students who know at least 3 programming languages. And here is 10. Because we are making 10 trials, we are asking 10 students whether they know 3 programming languages or not. The number of successes that we consider here are 5, because we are interested in knowing the probability of 5 of 10 students knowing at least 3 programming languages. The probability of success as specified in the question is 1. This is derived from the fact that 10% of this population has this characteristic. So the number of the probability of success is 0.1. The probability of failure is the complement of it, which is 0.9. And then we need to compute probability of x being equal to 5. For this, we use the same expression, the PMF function. We choose 5 from 10. P, the probability of success is raised to the power represented by the number of successes, which is 5, and Q is raised to 10 minus 5. And we get this answer, which is 0.00149, which is a very small probability. If we convert it into percentages, it is 0.149%. It's the chance that out of 10 students, 5 of them would be knowing at least 3 programming. Let's have a look at another example. A recent survey showed that 17% of the Pakistani youth have severe depression. If 10 young Pakistanis are randomly selected, what is the probability that 50% of them have a depression? Now, this is a very similar question, but it has been posed slightly differently. Here we see percentages. Here we do not see exact mention of the number of successes we are looking for. And the probability of success is 17%. So if we can model this as a binomial random variable, because there can be any youth that we observe can have one of the 2 outcomes, either he or she does have depression or they do not. So this is a success and failure criteria. Then we are making trials which are independent, because every other person who has depression is independent of whether the early person that we asked this question from, whether or not they did have depression or not. So here the number of trials is 10, because we are selecting 10 people. The number of successes that we're considering is 50% of the number of trials. So here it is 5 again. Then we have P as 0.17, because 17% is said to be the proportion of people who have the depression. And then the complement of it is Q is equal to 0.83. We need to find out the probability of X being 5, which is, in simple words, the probability of having 5 people among the 10 selected people who do have the symptoms of depression. So here, we compute P of X is equal to 5. Here is a typo. So here we compute the probability of X being 5, and we use the same PMF function of the binomial distribution. Probability of X being 5 comes out to be 0.01409. So another question is, what is the probability that at least 2 people have depression? Now, this question involves a range of values of the values of random variable. We need to find the probability of at least 2 people having depression, which means at least 2 means there can be, out of 10, it can be 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we need to find out the probabilities, all of these distinct values of X. And since this is a random, discrete random variable, we need to find the probabilities separately for each of these points, and then we add them together. But we can make use of the laws of probability to make this calculation a little simpler and quicker. Here, P of X greater than equal to 2 can be computed using the law of complement, which is that it is the same probability as 1. If we subtract the probability of people who, of this, the number of people having depression being less than 2, is the complement of this condition of X being greater than equal to 2. So we can use the law of complement. So this is same as 1 minus P of X being less than 2. Now, this probability is fewer points that we will have to compute. We need to compute probability on 0 and 1. So it's only 2 points on which we compute the probability, we add them, and then through law of complement, we can find out the probability of the desired interval. So here you see we need to find 2 probabilities. P of X is equal to X at 0 and X at 1. P of X at 0 comes out to be 0.155, and P of X equal to 1 comes out to be 0.318. We add these probabilities together and we get the probability for P of X is less than 2 as 0.473. Now we can compute the probability of X being greater than or equal to 2 by using the law of complement, which gives us this value 0.527. So there's a 52.7% chance that out of these 10 people who are randomly selected, about exactly at least 2 of them will be having the signs of depression. Since every random variable has expectation and variance associated with it, a random variable which is modeled by binomial distribution, which is a binomial random variable, also has expectation and variance. And the expression for expectation is n into p. Mu, or the mean of this binomial distribution, which describes a population, is computed by multiplying the number of successes with the number of trials. And this is, by the way, recall that binomial distribution has only 2 parameters, which were these n and p. So n and p can completely characterize a binomial distribution for a given population. We only need to know n and p to characterize the complete distribution. You can draw the plot. And the variance is computed as n, p, and q. For the standard deviation, you just take the square root of the. This is an example of calculating the expectation. Here we have a bag which contains 5 red, 4 blue, and 6 green marbles. If 4 balls are picked from the bag with replacement, what is the expected number of green balls in them? So since we are picking the balls using the with replacement strategy, the trials or the successive draws become independent. And this is a condition for the binomial distribution. Also, the outcome is either a success, which is we see a green ball, or a failure if we do not see a green ball. So the probability of success is 6 by 15 because we have 6 green marbles and they're being drawn with replacement. So the probability of success remains same across the different trials. We get it as 4. The total number of trials that we are making is 4 because we're picking 4 balls successively, one after the other. And by using this expression, the expected number of green balls in 4 trials is 1.6. Using this expression, n into p. And the same way you can calculate the variance and standard deviation.